of Pennsylvania. He got his PhD in Cambridge, and then he held postdoc position at Berkeley, at the Max Planck Institute in Garching, and at the Fermilab. Then he moved to Pittsburgh for a faculty position, and after that he moved to Penn, where he is a professor now. He's an expert in models and statistics of the large-scale structures, which allow to constrain models of galaxy formation and cosmology. And today he's going to tell us about his work on acceleration in cosmology and galaxy formation.
Thanks, Elena. I would say it's lovely to be there in Waterloo, but it's lovely. Thanks a lot for the invitation. I think I was thinking back, and I think Mike Hudson will be one of the astronomers who's known me the longest. And I'm not sure he was there when I actually submitted my PhD thesis on this day, the 17th of March in 1994. So that was a long time ago. Anyway, it's lovely to be talking. I was going to talk about two different things, both having to do with acceleration. And although in my abstract I said, time permitting, I'd talk about the galaxy formation one, I thought I'd try and do the galaxy formation one first, because it is shorter, and then do the acceleration, the cosmology one next. And so the first one is stuff that's mainly with Asim, who's at Ayuka in India. And then the one on cosmology is with Farnik Nikakhtar, who's at Penn, and Idit Zahavi, who's at Case. So the radial acceleration relation. So this one is a funny project for Asim and I. So we were working on making mock catalogs with realistic colors and other galaxy properties in the low redshift universe. And one of the things Asim added to it was H1 functionality, right? So given a halo catalog from a simulation, you can populate those halos with galaxies with a range of luminosities in different bands. And then with those different bands, you use that to help you decide which ones have H1 and which ones not. And so he had this mock catalog with all these properties. And so there has been, for a while in the literature, discussion of the evidence for dark matter that comes from rotation curves of galaxies, and a robust way of showing that is a plot which shows the acceleration that you observe, so the rotation curve that you observe, so v squared over r, so that's like an acceleration, versus what you expect if it were all due to baryons. Okay, so this thing's called the radial acceleration relation when you plot what you observed versus what you expected based on some estimate of the baryonic mass. Okay, and the shape of this thing in data has often been used to say that it's a challenge for cold dark matter models. And so part of this discussion is, how do observers actually estimate the baryonic mass? How are we sure that all systematics are okay in the rotation curve measurements and stuff like that? And so our goal was to do just the most naive thing in the mock catalogs that Asim had, which was to actually measure these things, assuming no observational errors and all of that, okay, and see how badly they did, okay. And then our hope was that we'd go and we'd study what sets the actual shape, what sets this, the scale, the scatter, all of that. Okay, so here's the kind of thing that observers do with the data, right? They'll have a rotation curve that they've observed. This is for a spiral galaxy, and this is from Lely et al. They will say there are different things that contribute to the mass that makes the rotation speed, the bulge stars, the disk gas, and that accounts for a certain amount, and what remains is dark matter, okay, or alternatives to GR. Okay. And so once they've done this, they can make a plot of, the observed acceleration. So here it's called G, it's the thing I was calling A on the previous slide. Okay, so this is V squared over R. And so each data point here is a data point on the right. And then they have an estimate of the mass in the baryons that made up the baryons here. So that's the acceleration from the baryons, and it traces out some curve. Okay. And so, the inner parts are where the acceleration is higher. And so these are the inner parts and these are the outer parts of the galaxy. Okay. And then you can do this for many, many different galaxies. And then you can ask, for the full range of galaxy types, do you end up with a big scatter plot or do you get a tight relation? Okay. And the surprise was that you got a reasonably tight relation that we'll look at in a second. That's what you do for spiral galaxies. You can do the same for ellipticals. The ellipticals have velocity dispersions rather than rotation speeds, but it's the same game. You've measured, well, now it's easier to, with these IFU data sets to measure the profile, the velocity dispersion profile. And then you will try to fit this profile using a combination of baryons plus dark matter. And then once you've made this fit, you can say, okay, now what happens if I plot, the observed acceleration, so the total acceleration and the piece due to the baryons. Okay. And so here's a plot of that thing. The only difference is, so this is like this top right panel. The only difference is that instead of plotting the acceleration total versus baryon, we're doing total over baryon minus 1, so the fractional. And so that would be like the acceleration due to dark matter, if it's due to dark matter, divided by the acceleration due to baryons versus the baryons. So that's this thing. Okay. And so this is again the data from Lely et al. That was found this very tight relation for the spiral galaxies. This is the measurements from Che for the ellipticals. And you see that they kind of sit in the same region in this plane. And there's not much stuff. The scatter is small around the plane. The relation that described the spiral galaxies quite well is one of these that's more curved. Okay. And the one that describes the ellipticals is a little bit flatter. Okay. But the basic idea was, how well do Asim's mocks do at recreating this thing? And so there's been, the mocks themselves were calibrated on relations that predate this RAR, okay? So they predate these calibrations of the radial acceleration relation. Okay, so they were calibrated back in 2015 on the basis of the abundance matching between stellar mass and halo mass, and then hydro simulations about what the gas, baryonic gas that is still bound but not in the form of stars does. Okay, and so the panel on the left is showing you for 3 different halo masses. So the blue is 10 to the 11 solar masses, green, orange or gold is 10 to the 12 and a half, and 10 to the 14 is the green. And then the different line styles are showing you, the total mass, the piece that came from stars, the piece that came from, so the C-gal is the piece that came from stars. To the stars, we can add the H1 gas, and then to the H1 gas, we can add the other bound gas or gas that was ejected based on calibrations to simulations, to the hydro simulations of what supernovae would have done. So this is all done without thinking about the radial acceleration relation at all. Now, one of the ingredients in these things is that, you start out with a dark matter halo, and that dark matter halo has baryons in it. And then what's going to happen is that the baryons can cool, they shrink towards the center. The dark matter is collisionless, it's harder for it to shrink towards the center. And so the baryons concentrate in the middle. And then then there's some efficiency with which angular momentum of the baryons is conserved and stuff like that. And so the crude way people think about this is to say the mass that was initially at some scale Ri can be at a final scale. And for the example I just used, it shrinks to a smaller scale R final. And the amount by which it shrinks is related to the amount of mass that was initially inside the initial radius to the mass that is finally inside the final radius. Okay, and if Q was equal to 1, if Q were equal to 1, then the minus ones would be, I wouldn't have to write them on either side, and this would be saying that R final times M final is R initial times M initial, and that's exact conservation of angular momentum. Okay, MVR is constant. So this parameter Q is just telling you how much things are not conserved. So Q equals 1 is perfect conservation, Q equals 0 is total violation. And so the idea is the initial mass was this mix of everything, and the final mass is a mix of everything, but it's been redistributed, right? So presumably on smaller scales, there are many more baryons and less dark matter, right? So it's baryon dominated in the center, and you can sort of see that in these plots, okay? Is that the stars contribute most of the mass in the center, but not much of the mass at the outside, okay? So in these models, because gas is being pushed out from the center and all this kind of thing, okay, the ratio of the final to the initial size need not be less than 1, meaning it's not obvious that the object shrinks. Okay, if enough of the baryons get pushed out, then there will be slightly more mass in the outer regions than initially, and that will tend to have, that will mean the final radius is bigger than the initial radius at some bigger scale, and that means that the object puffed up a little in the center. Okay, and so these are models that will allow, so that's why I've called them adiabatic relaxation rather than adiabatic contraction, because they will also allow for expansion. Okay, and so all we've done is we've just made a plot of what the typical scale, the expansion or contraction relative to initial is for the different halo masses, for the objects that were in halos of different mass. Okay, and so again, this is all calibrated in 2015. So now we can plot, right, the ratio of the total to the baryonic mass, and remember the total is M total over R squared, M baryon over R squared. So the R squareds don't matter here really. So when you plot it this way, it's really just the total mass over the baryonic mass. And this is the baryonic acceleration, okay? The color codes are what Asim measured in his mocks. And the solid line is the one that Che measured in 2019. And the dashed line is the one that was for the spirals, okay? And so the more recent determination actually sits bang on the mocks, or vice versa, the mocks sit on the data, okay? So I was sort of shocked, right? There was no work that was done to get the match. And so that's like saying this radial acceleration relation emerges pretty naturally in the context of lambda CDM. Okay, so we looked a little bit more at this problem, and we found that we could get some sort of pretty clean picture of why, not of why it worked, but of where the radial acceleration relation comes from. Okay, and what you can do is you can say, well, one ingredient is what was the initial mass, okay, the initial mass profile. And the initial mass profile would normally be something like an NFW profile or an Einasto profile, but it turns out that you can approximate it with a Hernquist profile, which is pretty similar. They're both, it's R to the -1 in the inside and R to the -4 on the outside. But if you scale where that transition happens, inside the virial radius, you can make it look like an NFW profile. Okay. And that's been known for a while. Okay. So a while means like 20 years. All right. And so it turns out that if you write this adiabatic relaxation equation, and you put here this expression for a Hernquist profile, then because you have an Ri here, and you have an Ri squared here, you end up with a cubic equation. And that cubic equation can be solved. It's cubic, so you can solve it analytically for any baryonic distribution. Okay, so that means the simulator can tell you what this quantity is, and you can just solve analytically what should be these curves. Okay. But once you have these curves, it means that you know what the mass, you know this ratio. Okay. Once you know this ratio, you also know the ratio of the baryonic mass to the total mass. And so you can predict, or you can solve for the shape of this radial acceleration relation analytically. Okay. And so I won't write out the solution to the cubic, but I'll just say that, so that's in our paper. But what you find is that acceleration, there's a characteristic scale, which depends on the acceleration of a halo, how concentrated it is, and the baryon. So this is the dark matter fraction, which is 1 minus the baryon fraction. Okay. So one of the things this shows you is that, it
probably, yeah.
Did someone have a question? No? Okay.
I think Alex's microphone is on, maybe inadvertently.
Okay.
But actually, sorry, Ravi, I did have a question. So it looks like you're kind of assuming things that you're not necessarily should know, because I mean, dark matter and baryons evolve simultaneously. So you're assuming that you know what baryons are doing, and based on that, you get what dark matter is doing. But how do you know what baryons are doing?
Oh, right. So these are the things that are coming from what people did in 2015 from the hydro simulations, right? So they say, oh, in our simulations, so they're giving us this thing. They're giving us what the baryons did.
Right, but they could also give you what dark matter is doing as well, because they evolve together, right?
Yes. So that, and in principle, that's what sets this number.
Mm-hmm.
Okay. And so from the simulations, we say there's a default model where there's a value for Q that we get from the simulations.
Right.
And there are the profiles of each of these components. Okay.
Mm-hmm.
And so the simulation has predicted everything. Okay.
Right.
And so in this sense, it has predicted a radial acceleration relation, just no one looked at it.
Okay.
Okay.
I see.
And then when we looked at it, then it matched very well the data or the observations. So the question then was, can we understand a little more why? Or can we understand a little more the structure, let's say, yeah, of what do we really learn from this match?
Mm-hmm.
And so that's why we started trying to do this analytically, right? To see how much of this emergence of the radial acceleration relation is, what are the ingredients that really matter, right? And so we sort of were able to split it into two pieces. Yeah. So by realizing that it's just a cubic equation, then the cubic equation sets a scale for you. And so that's this scale. And so what this scale is really telling you is, what is it about the dark matter that matters? Okay, and so there's obviously the acceleration of the halo. Okay, so that's setting an overall scale. But what also matters is how concentrated the halo is. Okay, and then of course the how how much is dark and how much is baryon, right? So, so this one is usually is 1 minus the baryon fraction, right?
Right. Okay, that makes sense. Thanks.
And so one thing this shows pretty clearly is that this thing, because it depends on halo mass, is not universal. And so the scale for clusters will be very different from galaxies. And so there has been some discussion, because the one for galaxies is so tight, there's been some discussion about whether this can be accommodated in lambda CDM. And so the answer is, well, if the one for clusters is the same as the one for galaxies, no. Right? Because the generic prediction is it will be much higher. And indeed, when we measure it in simulations, it is much higher, right? But the measurements in data, there are just a handful. There were a couple just recently also show a big offset for the clusters. And so it seems like the lambda CDM scaling is there in the data too.
Which is, I guess, similar to saying that MOND doesn't work for clusters, right?
Yes, there's an interesting discussion to be had in that direction, okay? So for MOND, and that's why I've been slightly careful in saying this, for MOND, they will worry that when they go, so if I have a galaxy and there's some big cluster here, or there's some other object, or this galaxy is in a cluster, then what should I be calling the acceleration?
Mm-hmm.
And so for MOND, they worry about what they call the external field effect.
Right.
Okay. And the external field effect modifies this shape. Okay, so the external field effect matters at small accelerations. So it's over here, and it makes a small difference. Of course, in our mocks, whatever is there is there.
Mm-hmm.
Okay, so there's no extra thing to account for because it's lambda CDM. I can talk offline about, or after the talk, about, there was a paper earlier this year or the end of last year about claiming a detection of this external field effect. And I can talk about my interpretation of that paper. Yeah. Okay, but at least on galaxy scales, the thickness of this acceleration relation then is coming from the range of halo masses that give rise to galaxies, the concentrations of those, and there's a scatter in concentration at fixed halo mass, so that's making scatter. And then there is whether this number, basically, the baryon fraction is constant across all objects. Okay.
And what about the Q? Is that universal?
Oh, good. I'm getting there, Mike. I'm getting there. All right. Oops. I hit the button too soon. So we'll get there soon. Okay. And so we in CDM, you're going to get small scatter just because when the mass gets big, the concentration gets small. And so these two conspire to keep the scatter small. Okay. And so that's why over the range of galaxy mass halos, it looks like a pretty tight relation. Okay. Now for Q, right? So that adiabatic contraction thing. Now in our mock catalogs, that was just a constant. Okay. And it was a constant that was set to the number that seemed to match the simulations. Okay. And that number is about 2/3. Okay. So it's in between 1, which is perfect angular momentum conservation, and 0, no momentum conservation and no contraction. Okay. And so here is, if in our mocks by hand we put Q equal 1, angular momentum is conserved, or Q equals 0. And so you can see that has a big effect, right? So Q is, the amount of, that relaxation parameter is what's setting the overall shape. And so if you conserved angular momentum, then you basically got this power law, and that's not like the observations. And if you had no back reaction at all, then you're curving away from the observation.
So what do you mean exactly? Because of course we have to conserve angular momentum. So
in
globally.
Globally. So that means in these things, what's happening is that you have energy loss and some angular momentum loss because gas actually is drifting out.
Okay, so it's like ejected from the system.
Yes, yeah. And so we actually have some gas that's sort of being ejected. Okay, that was true in the simulations. Okay, and so we have a piece in our mock catalogs that models that. And that ejected gas, had I shown you this density profile, is basically, you know, as a function of R, is basically just, is pretty flat across the whole thing, right? So the density of ejected gas as a function of R is pretty much uniform, which means it just got blown out everywhere. Okay. And so to me, the main surprise was that it actually worked out, right? Because there's quite a discussion in the literature about whether lambda CDM can do this at all. And we didn't tweak anything, right? And so now at least we have a sort of framework for saying, okay, if we wanted to start tweaking, what are the effects going to be, right? So changing how the simulations do this lack of perfect angular momentum conservation, stuff like that. What effect will that have on this RAR? And so I just wanted to leave you with that, right? That there's some sort of analytic understanding now of the shape of this thing. The shape comes from relaxation physics. The scale comes from the baryon to halo relation, and the scatter is mainly the halo concentrations. In our mock catalogs, that's because the baryon fraction and the relaxation physics, that parameter Q, they were both constant, right? And so there was no scatter coming from these guys. Okay. So that was it for my galaxy scale stuff. And so now I'll switch to the cosmology stuff. So I don't know if we want to talk a little more about this, or I make the switch and we can do questions at the end. Questions at the end?
I'll save it to the end.
Okay. All right. So now I'm going to switch scales, and I'm going to talk about baryon acoustic oscillations and how they're used. So not how they're used, but just they are used to constrain the expansion history, and so the acceleration of the universe. Okay. And the beauty of this probe, as you guys in Waterloo know really well, is that it's a probe that can be used at many different redshifts and uses basically the same physics at many different redshifts, right? So, and so this is, the probe derives from the CMB, the interaction between photons and baryons when the universe was young, and so you know there's this nice animation by Eisenstein, Say, or White that shows if you had initial spike of dark matter and baryons and photons, then the photons will start spreading out and they will collide with the baryons and move the baryons outwards, but not the dark matter. And so at some time later, you will have a shell that's propagated out from this initial spike. But then after the universe is cooled sufficiently, the photons stop pushing those baryons. And so you have this shell, okay? And the radius of the shell depends on how efficiently the baryons were pushed by the photons and the time that they were pushed for, right? Which was roughly 300,000 years, okay? And so that sets a length, and that length expanded 1,000 times since the CMB was formed, is about 100 megaparsecs today. And so this length is the one that people want to use as a standard rod. And the only complication is that in reality, we didn't have one single spike from which the photons went out, but we have many different spikes. And so there's a big mess, okay? But we can still look for this feature statistically. And we can look for this feature in the galaxy distribution at different redshifts. Okay, there's the cartoon, right? Around each blob of baryons, there should be this tiny shell of baryons, 100 megaparsecs co-moving away. And then in reality, it's going to be a little more complicated than this, because you'll actually be looking at many different distances. And so the same physical scale will be different angular sizes on the sky. And that's what's letting you map out the expansion history, right? So it's the angular diameter distance relation. Okay, there's also a component in this direction rather than this direction, but that's the logic, right? You get to do a geometrical test with this standard rod. Okay, the way the rod is usually presented is in terms of the power spectrum of galaxies. And so here is data from the CMAS survey showing the power spectrum. And the way I like to think of this is, as Elena knows, I like always to think in real space. So I think of this as a shell in real space. And that shell is the difference of two spheres. And if I take the difference of two spheres, so the difference of the two spheres is this shell in real space. And so, ideally it's something like that. And if I take the difference of two shells in real space and that shell is thin, then the Fourier transform of that thing is sine kr over kr. And the r is this scale. So that's the BAO scale. And so if I think of this as a smooth curve with a kind of delta function sitting on it, then that will be a smooth curve with oscillations sitting on it. And the oscillations are from this guy. Okay. And so this is the thing that people use as the standard rod, either the position of the rod or the wavelength of these oscillations, right? Because it's that scale there. Okay. Okay. And so this is how you map the acceleration history, okay, by doing this at different redshifts. So the only thing we've got to be sure of is that that rod, which we see in the CMB, is not changing size with time, okay? And so here are simulations showing you structure formation in the universe. So let's look at that quickly again. And the basic idea here is that if your rod was 100 megaparsecs in size, nothing has actually moved 100 megaparsecs, right? So all of the structure formation is pretty local, and so there's some hope that the rod survives, okay? And that's because we live in a universe that is cold dark matter dominated, and so the typical speeds are not relativistic, okay? And so that means that the late time field retains memory of the initial conditions. On 100 megaparsecs, that's certainly true. And then I have a quick aside about some other work that I've been doing with Marcello Musso, who's at the East Africa Institute for Fundamental Research in Rwanda. And so one of the things that we've done is we've asked, if the late time field remembers the initial conditions, then the places where galaxies form are dense nonlinear objects. So they're the dark matter halos, and in those halos, where did those halos, what was special about where they formed? Okay. And there's an old literature that says, well, maybe you should think of a halo because it's a dense patch today. It's 200 times or more the density of the rest of the universe. It was probably a dense patch in the initial conditions. And so there's a very beautiful history of using peaks in an initial Gaussian random field to model the special places where halos formed. Okay. And a lot of that work has concentrated on being peaks in the density initially. Okay. And Marcello, he made the point that a peak in the density is not necessarily a peak in the initial energy, the potential plus kinetic energy in the initial conditions. And in particular, maybe what you really want is to find those positions in the initial conditions where particles are all converging to the same position, because that's what's going to make a halo. And it's not obvious that that's the place where the density is highest. And density being highest might be a good bet, but it may not be optimal. Okay. And so we did a simple thing. We just said, what happens if we look, if we do the following? You run a simulation, you find the halos, you find the particles that made the halos, you take each halo's particles and you trace back where they were initially. And now you ask, where they were initially, are they peaks in the density field? Are they local maxima in the density field? Or are they local maxima in the energy field? Okay.
Sorry, I don't understand that, Ravi. What do you mean? I mean, particles are all over the place. So what is supposed to be the peak?
So you ran your simulation and you found a halo. So this halo is made up of a whole bunch of particles. Now you can map this back to the initial conditions. So the initial conditions, this was a bigger patch, and the particles were, more or less, like that, right? And so for this thing, you can now say, I want to calculate for this initial patch, what's the average, what's the density of this patch? There are other particles here that are not part of what we call the proto-halo. Right. But I'm still allowed to compute the density. Suppose this were a sphere smoothed on this scale in the initial conditions. And then I can compare it with the density smoothed on this same scale, but at a slightly different position, right? And I can ask, is it higher here than here?
Right. Okay. I see.
And then I can do the same, but instead of computing the density delta here, I can instead compute the energy, which I'll call epsilon. Okay.
And what is energy?
So energy is it's the combination of the potential energy, so Gm over R with respect to here, and the kinetic energy. Each particle has a speed, right?
The linear kinetic energy.
All the linear, everything linear, because now we're in the initial conditions.
Okay.
And so it turns out that because you're in linear theory, these two quantities are related to each other, but they're not the same. Okay. And I'll say a little bit about how different the two are. Okay. But just to see if this is worth doing, here is a bunch of, 25 halos mapped back to the initial conditions of 25 proto-halos. And then we're looking at the density smoothed on this patch, right, as a function of, for the different positions, okay? For massive halos, you can see that the density does peak at the center of the proto-halo. But so the numbers show you they're a measure of the mass of the halo. And so here you can see the low mass halo, the correspondence between density peak and halo center or proto-halo center is not very good. Yeah. And this is what happens if you do it with energy instead. Okay. So density, energy. And so the energy seems to be doing a much better job of, so saying an object should be a peak in energy is a much better approximation to the patch, to saying what's special about what makes a halo. And so this is one example of, the way in which the initial conditions, the memory of the initial conditions persists all the way to the present time.
But isn't this a little bit cyclical, because you're computing energy with respect to the other particles of the halo? So that suggests that you already know where the halo is, so that you can compute the energy with respect to
Yes, because, well, fundamentally what we did was we actually found the special particles by running the simulation in the first place, right? Right? And then we traced them back. So you're right, this is circular, but the point is that the thing that is special is the energy and not the energy is more special than the density. That's the point. Yeah.
Mhm.
So if you're going to do peaks theory, you should do peaks theory of energy.
But my point is that the peak, it's not a local quantity. You have to know where the other particles of the halo are to define the energy with respect to them.
Yes, but in linear theory, it boils down to smoothing the particle distribution with a different smoothing window. So we're used to saying you should smooth with a top hat smoothing window to define the density. And the energy just corresponds to changing this smoothing window. So that was part of the work in the paper, was to show this. Okay. And so that's what makes the difference. So one of the nice things is the actual analytic complication to doing these predictions is 0 compared to density, right? It's exactly the same mathematics. The only thing that changes is the smoothing window. And so that's kind of a nice thing. But of course, because the smoothing window has changed, variances and spheres and all that stuff has changed. So quantitative predictions will change. But the work to get them is no different.
Is it because we are somewhere like in Newtonian regime? If we did relativistic calculation, then we wouldn't have to worry about this. Or...
Yes, I guess so. But we're on such small scales compared to those where the relativistic thing really matters that it doesn't arise. Yeah. So these are tiny patches compared to the big ones where relativistic effects matter. And we're not in the regime where we've made black holes, where we again then care about relativistic effects.
Right, but I mean, if it was, yeah, okay, I'm having a hard time understanding why would the kinetic energy matter, but if it's not relativistic.
Oh, I see. No. It's just because in linear theory, some people like to think of structure formation as being purely because of the motions of the particles. So you really start from cold, and all perturbations are driven by the motions of the particles. And so for them, everything is motions. So that's why I was saying it that way. But the fundamental thing is you have a density fluctuation field, and you can smooth that with one window to get average density. And if you change this smoothing window, you will get the thing that in linear theory we call energy in the Newtonian limit.
Okay.
But so this was just an aside to say there is memory of the initial conditions, even in highly nonlinear objects. And so back to our problem of memory of the initial conditions at 100 megaparsecs. And so we expect that memory to be retained, okay? And so there was a very nice illustration of this about 10 years ago by Nikhil Padmanabhan, where they did a simulation and they highlighted, with a bunch more particles, a spherical patch, and they watched how it evolved as time goes on. And by redshift 0, that patch has distorted a little bit, but is still pretty much the same size. Okay. So the radius of the patch is our 100 megaparsec rod, but how clearly defined that radius is determines how significant this feature is. And so the motions between redshift 1000 and now have made this thing fuzzy, and they have sort of smeared out what was otherwise a delta function. Okay. And so this effect is what a lot of work has gone into reversing in the data, okay? Because it means that in the data, this bump is not as clear as we would like it to be. Of course, the higher it is, the easier, more signal to noise in the measurement, that kind of thing. Okay. And of course, we'd like to be sure that the thing hasn't shrunk, even by a little bit, because now we care about percent or sub% shrinking. Okay. And so the main effect is the smearing. Okay, is that the pristine thing from linear theory has gotten squished down because it got broadened and smeared. Right? And so the hope is that even in the smeared thing, we can measure a scale that corresponds to that standard rod scale. Okay. So how do you estimate the scale? And of course, you don't want to differentiate the data. So you have to do more sophisticated things. So the standard thing that is done is to fit a model, a lambda CDM based model, to either the power spectrum or the correlation function, or to first try to undo the smearing by saying, well, we know that gravity has made the particles cluster together, so let's try to reverse the sign of gravity and move particles back, reconstruct the initial density field, and then fit a model to the correlation function of the power spectrum. So in either case, you use a cosmological template that you then fit to the measurements. And so what I'm after is, can we be a little less model dependent? Okay. And so this will happen in 2 steps. We'll first say, how do we handle the convolution or the evolution, because it's actually a little more than just convolution. And then once we've done that, what next? What do we use as the rod? So the idea is that supposing you wrote the linear theory correlation function as anything. So in this case, as a simple polynomial, okay? And so if this thing is a simple polynomial, then the smearing, because of the particles moving, that's a convolution of the initial separations R to final separations S. Okay. And so it turns out that if this kernel, the smearing kernel, is a Gaussian, then this can be done analytically. And so when you do this, then the coefficients, of course, come straight through. And then the result of this R with this Gaussian kernel is sort of like taking a moment of a Gaussian distribution, right? Only complication is it's actually a 3D Gaussian. And so it's not moments of a Gaussian, it's moments of a non-centered chi-square distribution. And that's what sets the shape of this function here. Okay. So these functions are called generalized Laguerre functions. It doesn't matter what they are. It's just important that you can write them down. Okay. And they're almost like polynomials, and some have error functions. Okay. And so that means that what you should do is you should fit the correlation function that you observe at some late time with this series to determine the coefficients AK. Okay. So these functional forms are preset, and you try to determine these. But to do this, you did need to guess how much smearing happened. Okay. So you guess how much smearing happened, 5 megaparsecs, 10 megaparsecs. You make that guess, and then you do your fit. Once you've done that, then these coefficients AK, you just plug into this expression here. And that does the deconvolution analytically. Okay, so you will get the linear theory correlation function that corresponds to the nonlinear one that you observed. And so this is the straightforward algorithm for doing the reconstruction if smearing were the only reason for the difference between the nonlinear correlation function and the initial one. Okay. In reality, there's another term that the specialists call mode coupling, and we put this thing into. Okay, and it's straightforward to include. I just haven't because it just looks messier. Okay, so let's have a look at how well this does. Okay, and so the crosses are the measurements. So that's the nonlinear correlation function with their error bars. Then we fit the crosses with their error bars. We get our coefficients AK, and we reconstruct the linear correlation function. So that's the pink stuff with the bands. Okay, and these bands are coming directly from when you fit something with error bars, then you fit with error bars, you get a best fit band, and that band, when you reconstruct, becomes this other band. Okay. The black is the actual linear theory shape. Okay, and so we've done a pretty good job at reconstructing the linear theory shape, but it's not perfect. Okay. Just for comparison, the dashed line shows you the method that's based on moving particles around and trying to reconstruct the initial conditions by actually moving stuff around. Okay, so this is the sort of standard that is used for most BAO analyses. Okay, and you can see that it does a very good job, right? So the binning was coarse, so you could imagine that this dashed line is sitting up here actually. Okay, so it does a good job of reconstructing the shape of the bump, but is not great at the shape elsewhere. Okay. All right. So this was for dark matter. So then you can ask, how does this work with biased tracers like halos? And so Farnick did the check for the dark matter is the stuff we looked at before, for low mass halos and for high mass halos. And in principle, the high mass halos are more strongly clustered. And so he's divided everything by a bias factor. So all the curves look pretty similar. And because he's divided by the bias factor, they should look like the linear theory shape. And you can see that the red bands more or less get linear theory. Again, not perfectly, but they've done a significant amount of the reconstruction. So they're significantly closer to the initial shape than before. Okay. So these were biased tracers in real space. Now we can look for biased tracers in redshift space, because now we can ask, supposing I had many different, we don't know how galaxies populate halos. Maybe there's some complication that arises in that. And so there was a whole series of ways. So there's a sort of a neat code that Duan and Eisenstein put together for populating galaxies with halos in a variety of different ways. And so Farnick looked at a bunch of those different ways of doing it. The black are the measurements. The gray shows our fit to the measurements. The pink is the result of taking, the A of k coefficients that we got here and using them in the simple polynomial to do the reconstruction. And you can see that it does reasonably for different biasing schemes. There were a whole bunch of biasing schemes, and I'm just showing you a couple of them to show you that the fits are always pretty good and they're never perfect. Okay, so this kind of systematic difference at around the peak is always there, and at around the dip is always there. Okay. Nevertheless, it's sort of encouraging that we're a lot closer to linear theory for very little work, right? Now, of course, we're doing a deconvolution, okay? And so the error bars will be expanded, and you can see that the gray band is narrower than the pink band, okay? And so you'd say, well, that's fine. You've made the shape closer to linear theory. Let me skip this. But if we want to make a rod, then not only do we want the rod to be unbiased, but we would also like to have small error bars that came with the rod. And so the concern is that by removing the bias, by doing this kind of reconstruction, you're paying a cost in increasing error bars. And that's sort of the motivation of the standard way of doing reconstruction, is to actually move particles around so that they're not doing just convolution. They're doing something much more sophisticated. And so the question is, can we get reasonable error bars anyway? Okay. And so here the philosophy is that we want to look for something that is not too distorted. So that didn't need much reconstruction in the first place. Okay. And so that means that we are not necessarily going to use the peak itself, the scale of the peak itself, as our standard rod. We're going to think of something else. And so here's the schematic. The correlation function has a peak and a dip, and there's a point in between. And we'll call that thing the linear point, okay, the midpoint between the peak and the dip. And so about 5 years ago, Stefano Anselmi made measurements in a simulation where he found, if he was looking at the dark matter correlation function at different times, redshift 2 down to redshift 0, if he scaled the correlation function by the fact that in linear theory it should grow, so you scale by the linear theory growth, then he found that the linear theory correlation function is gradually getting smeared as particles move more and more and more down to redshift 0, okay? But this position didn't evolve, okay? So the height of the peak is changing a lot because of the smearing. The height of the dip is changing a lot because of the smearing, but the point in between is not changing. So that's our first hint of what we might use as a standard rod, is a thing that has evolved much less. Now, to be fair, when people use the peak, it's more like the location of the peak, not the height of the peak, that matters. Okay. And so we'll come back to the location of the peak rather than the height of the peak in a second. Okay. But for sure, the location of this midpoint is pretty well behaved. And so I want to try to exploit that. Okay. And I want to try to understand that as well. Okay. And so our simple way of understanding that is to say the nonlinear smearing in Fourier space is like a multiplication, e minus k squared. So that's a 1 minus k squared. So the first correction to the shape is because of this k squared.
Ravi, excuse me, just
Yeah.
to let you know that we passed the hour. If
Okay.
you were able to wrap it up in a few minutes,
I'll be
that
2
would
minutes.
be great.
I'll be 2 minutes. Yeah. And so this k squared is like a Laplacian. And a Laplacian means that it's a first and a second derivative. So at the position of the maximum, this first term is 0. So at the position of a peak, this is 0. But the second derivative can be big. After all, it's a peak, so it's pretty curved. This is the thing that's suppressing the peak. Okay. At the inflection point, this term is 0. And so this is the term that survives. Okay. But this term, if we take this term and we write it as a dimensionless thing times another dimensionless thing, you'll see that the suppression depends on how much smearing there is compared to the scale of the BAO feature, this thing squared. And so this extra correction is small. And that's why the inflection point, which is kind of the midpoint between the peak and the dip, is not affected by nonlinear evolution. So I want to take that insight and to say k squared is also the leading order term to any kind of galaxy bias, halo or galaxy bias. And so that means that this point, this midpoint, this linear point is immune to the scale dependence of bias as well. Yeah, so the leading order changes to the shape of the correlation function. The linear point is insensitive to. Okay. And so what Farnick did, so I will skip this, and I will just show the final slide, where Farnick made a bunch of measurements of, here now there are 4 different HOD models, 4 different galaxy models in boxes that are each a gigaparsec in size. And so for each box, he measured what is the scale of the peak and what is the scale of the linear point. Okay, and so that's this set of curves here and this set of curves here, right? So what you can see is that the correct answer, the answer in linear theory is here, and so the peak position has shifted by quite a few megaparsecs, by a few percent. This is the shift that all the reconstruction algorithms are trying to undo. Okay, and they do it well. Okay, so the solid curves show you the standard reconstruction of the peak position, which is the BAO standard rod. But there was a lot of reconstruction that had to be done. Okay. In addition, the position of the peak in the nonlinear field, there's quite a large variation. So the position of the peak cares about different galaxy assignment algorithms. And that is reduced somewhat by the reconstruction algorithm. Here is the linear point. So you can see that the linear point shifts much less than the peak position does. Okay. And once reconstructed, there's a lot smaller scatter. So it's much less sensitive to different halo bias schemes. Okay, so it's robust. Right? And so these things, they were not things that the standard reconstruction was even made to get right? It's trying to get something that's closer to getting the peak scale right. But it does the linear point very nicely. There's a slight bias, right? It should be here, but small scatter. So that's the standard way of doing things. And this is our Laguerre way of doing it. So now I've expanded the scale because I'm not looking at the peak scale, just at the linear point scale. And so here's the offset from the answer that it should be, and then here's the value once we've done the reconstruction. Okay. And so there's no offset, and a measure of the error bar would be the spread from here to here on the scale, on the distance scale, and that is not broadened in our reconstructions compared to initially. So we didn't pay a big price for doing deconvolution because there wasn't as much to be fixed in the first place. Okay. And so because this method is so straightforward, you're just fitting basically polynomials to the measurements. There's no extra simulation step to be done. I'll just skip this. And because the linear point is robust to different galaxy bias schemes, it seems like a useful extra tool in the bag for using BAO to constrain cosmic acceleration. Yeah. And so we're currently on the lookout for synergies between this simple Laguerre reconstruction stuff with the standard methodology. And so I'm sorry I went long, but I'll stop there.
All right, thank you, Ravi, for the nice talk. Are there any questions for Ravi? You can just unmute yourself if you have questions.
Ravi, you said you could talk offline about the claims of detection of the external field effect. Are you willing to say anything online about that?
Sure. Yeah, what I really meant, I didn't want to use up too much of my talk time. So let me slide back to those slides. So really, those claims boil down to the following. They notice this. So they notice that this sort of curls down a little bit from the purple relation, okay? Now in lambda CDM, it curls down, okay? And it has, there's no new physics. It's just something that happens because of the shape of, because of this default shape and stuff like that, okay? The way the external field effect is motivated is to say, let's now take this suppression and correlate it with the large scale environment. Okay, so they went to each galaxy. They went out to the two mass, what's it, 2m plus plus, and they used that to model the velocity field, and so estimate the large external acceleration that this particle feels because of this mass around it. And they found a correlation. Okay. And so they said, oh, the external field is causing this. That correlation is evidence of the external field effect. For us, for lambda CDM, because we get that curvature without any extra effect, right? For us, it's a consequence of the fact that I think on this one I said mass is kind of increasing this way. Okay, it's increasing upwards. Oh, sorry. And so for us, low mass is here and high mass is here. And we know that low mass has a low bias factor. And a low bias factor means there's less matter out here. And so if you go through and you say, what's the acceleration? And there's sort of a very simple linear theory way to say it, right? In linear theory, the acceleration is basically the net infall speed, okay? Because the infall speed over time is an acceleration. And this infall speed is basically a bias factor times the infall speed for dark matter. And the infall speed for dark matter is the volume average of the correlation function, okay? And so we would have said, you're going to, in lambda CDM, you will get a correlation between this downturn and a large scale acceleration because of this. And you'll get the right thing in lambda CDM because we know that as we go to very large scales, there's no external effect, right? The acceleration should be 0. But if you decided to evaluate this on a finite scale, you'll get a correlation, right? If you truncate this volume integral. And so they went out, a few hundred megaparsecs, and so they found a correlation that for us is because it correlates with mass. So it arises, if you want, it arises very naturally in lambda CDM, whereas it's an external additional effect in MOND. Did that make sense?
Yeah. I guess I had wondered whether there was any, also relationship with concentration, but it sounds like not necessarily.
So I guess we didn't really look for that. There is a sense in which, so if you go with this idea, then you can ask, so bias is primarily a function of halo mass, but people are interested in this phenomenon they call assembly bias, which
right
depends on concentration, and so there will be an effect, right? But the dominant one is with mass.
Okay, thanks.
Yeah.
So may I ask a question? So this
Sean?
is Sean speaking. Hi,
Sean.
Thank you for a great talk. So I have 2 quick questions. So there's a recent paper by this Lucy Smith and Hirna Pierce on machine learning and the initial condition and late time. And they assert that we only need the primordial overdensity to predict the late time halo distribution. Do you have a comment on this, or this energy exclusion set theory of energy in peaks, maybe an idea to study this?
So
yeah.
I'm not sure how recent the paper is that you're talking about, because I did have a correspondence maybe a year ago with them
Yes,
about
so-
using machine learning to play this game. They were almost trying to do the excursion set game, right, of smoothing on different scales. That's the one you mean?
So it's Nature Communication in November 2000, last year.
Yeah, it might be that
Maybe
one. But the so I guess there's a couple of things. The first thing is because this is the difference between energy and density is just a slightly different smoothing window. So for the density, the smoothing window is is KR. Okay.
Right.
And for the energy, it is 15J2 KR over KR squared. That's the only difference, okay? And so depending on how the test was done, using Fourier modes, you won't see a difference because it's the same density Fourier modes. Whereas if the smoothing scale actually matters, well, the same smoothing scale is there. So there are subtleties in the actual shape of the smoothing window that make a difference, but the broad brush will be similar density to energy. My main concern with what they were doing was that, unless it was modified, but earlier versions of their stuff was, when you do the excursion set, when you play the excursion set game, you choose random positions in space and you draw smoothing filters and you calculate stuff inside as a function of smoothing radius. But you treat, you make the statistics of every single position in space, okay? Now, we know that except for the position that ends up being the center of the halo, so the center of mass position, if you want, in the initial conditions, all the other positions give you the wrong prediction.
Right.
And that means, so if you're using all of these guys to train your machine learning algorithm, you're using a very noisy training set. Okay. And I don't think you will see any subtleties like this difference between smoothing windows and stuff like that. Okay? And so at least my correspondence with them was to say, try to train just on the center of mass particles to see if you see something significant there before you go to all of them. Because we know that all of them mainly add noise in the excursion set picture, right? And in fact, that's why in the analytic models, I moved from doing excursion set to doing excursion set peaks and worrying about what these special positions are in the initial conditions around which we should be doing the smoothing. So this is a very important step. It's a weird step. It was a step that Dick Bond made in 1988 before the excursion set paper of 1991.
Right.
And people just sort of forgot it. Once the excursion set paper came out, they stopped working on this excursion set peaks. But I really think the excursion set peaks is the nicer way. Right. And then if you want the main difference between what Bond did in 88, he was working with excursion set peaks in density, and we're just doing it with energy because it looked like energy was better than density.
Right. Thank you. So I don't know if I have time or if I keep it for the last, yeah, if there are other questions, I ask that. So may I ask the question, the second question? So, okay. So observationally, is it easy to calculate and predict the linear point? I mean, observationally, you have the dip and the peak in the same time and then go to the linear point. Am I right? Or?
Yes. Yes. So observationally, so I mean, so here are measurements from CMAS. I didn't have time. So the x-axis is a little confusing, but just think of this as distance. Okay, and so this should be the 100 megaparsecs. So the measurements are the symbols with the error bars. And so what we had done a couple of years ago was just fit this with a polynomial. That's the smooth curve. And from fitting with a polynomial, you can get this linear point. Okay. And from fitting with the polynomial, you can get its error bar. And so this now compares our measurement of this linear point for the distance scale with the one of the collaboration once they had done their reconstruction. Okay.
Right.
And so it's straightforward to do. Back then, the error bar was 1%. In the future, we're going to sub%. And so back then, we weren't so worried about reconstruction of the linear point. It was accurate enough. And so here it says the linear point was shifted by 0.5% longwards of the actual measurement. Okay, so we measure this linear point, we multiply by 1.005 as a crude way of accounting for the smearing. Now that we want sub% precision, that's why Farnick has done the stuff with the lug errors.
Right. Okay, thank you, Ravi.
Yeah.
So I guess we can thank Ravi again for the very nice talk. And I'll see you all